Welcome back. Now that we have the main pieces of the address controller set up, we'll start wiring up the control signals that interface with the eventual control logic. The operational characteristics are somewhat complicated, and I've been trying to think of a way to cleanly explain the order of operations. But after multiple reattempts at making this video, I think the best way to learn how it works is to first build the module completely, then explore the completed module afterwards. So let's start from the top down. Program counter out high and low connect to the control buffers. Remember that these pins are active low, so we'll need to add inverters to handle that. PC load also needs to be inverted, and it goes to the load input for the program counters. The clock gets wired directly to the program counter clock inputs, but we can't directly connect these to the MAR. This is because the MAR chips don't have enable pins. Because of this, we need to create our own enable circuitry using the MAR input pins. First, we'll invert the clock input going to the MARs, then we'll use a NOR gate between the clock and the MAR load pins. The output of that NOR gate then goes to the clock inputs of those MAR chips. This ensures that the MAR only loads values when we want them to. For PC clear, this should be inverted and then routed to the program counters. We'll also route these to the MAR chips, but in the real hardware, the MARs don't have reset lines. Next, we have PC count. This goes directly to the low program counter register, but the high program counter should only increment when the low counter has overflowed. Once again, the program counters themselves only have a single enable pin. If we just wired the overflow output of the low program counter to the high counter, there's a condition where if the low program counter contains the highest value it can store and the PC count line isn't enabled, the high program counter will continuously count up forever. This isn't the behavior we want, so we need to gate this overflow line and the PC count input through an AND gate. That output from the AND gate then goes to the high program counter enable pin. This is a behavior that's unique to Logisim. The real hardware doesn't have this AND gate, because the real program counter chips have separate enable lines and overflow input pins, which Logisim doesn't have. Now when I do the same test again, placing the largest value into the low program counters, and then cycling the clock with PC count disabled, the high program counter is inhibited from changing until PC count is enabled. Moving along, we have the MAR select, or MAR cell for short. Very simple. This goes directly to the output multiplexer. And finally, just because I completely forgot about them, wire the raw outputs to their respective splitter outputs. And that's it. That's all the control logic for this module completed. Now we can go in and play around with it to see how it works. First, be sure to save your project. Next, go in and set all the active low inputs to high. Now cycle the clock input a few times. You should see no changes being made to the program counter or to the MAR. Next, enable PC count, and cycle the clock a few more times. Program counter low should increment once per clock pulse. Now disable PC count, and on the data bus input, set all the bits to high. Next, set MAR-L load to low to enable it, and then cycle the clock one time. Then set MAR-L load back to high. You should see that the value has moved into the low MAR register. Set the data bus input to the value 7. And then repeat the same steps for the high MAR. The MAR should now hold the value 07FF in hexadecimal. Next, enable MAR cell and set PC load to low to enable the parallel inputs of the program counters. Then cycle the clock once. The program counter should now accept the value from the MAR. Now set PC load back to high, set PC count to high, and cycle the clock once. The program counter should now contain the value 0800. Now set marcel to high. You should see the old 07FF value output onto the address out bus. Then set marcel back to low. Next cycle both the high and low program counter outputs. You should see the program counter values output onto the data bus output. Finally, cycle PC clear, and this will asynchronously clear both the program counter and the MAR. At this point, if everything lines up, the address controller is fully functional. Again, not everything is going to make sense until we get deeper into this build, specifically when we get to creating the mega code for the control logic. But now we're ready to interface with the EEPROM and the RAM, which we'll cover in the next video.